Imagine you just hired a new lead analyst for your team.
Okay, I'm picturing it.
Right. And they are undeniably brilliant. I mean, they can crunch complex numbers in seconds. They spot trends nobody else sees. And, their baseline accuracy is just off the charts.
Sounds like a great hire, honestly.
You'd think so. You're thrilled. But then maybe a few weeks in, you start noticing this really terrifying habit.
Uh-oh. What kind of habit?
Well, when they don't know the answer to a critical question, they don't say, oh, I need to check on that. Instead, they look you dead in the eye and with total confidence just smoothly hand you completely fabricated data.
Oh, wow. Yeah, a flawless delivery of a total lie. That is incredibly dangerous.
Right. Especially when it comes from someone you've, otherwise learned to trust.
Absolutely.
Yeah.
Because you stop verifying their work.
Exactly. You'd almost rather have an analyst who is a little less smart, but who actually knows when they are guessing. And welcome to the deep dive. Today, we're trying to figure out how to fix these massive, inflated AI egos.
It is such a huge problem right now.
It really is. We've got our hands on a brand new conference paper heading to ACL 2026. This is from researchers primarily at the Chinese Academy of Sciences and Tsinghua University.
Yeah, it's a fascinating read.
It's about a system called CAPO, and it basically completely rewrites the math on how we teach AI, to be honest.
Yeah.
So, okay, let's unpack this. Our AI models are getting insanely good at math and reasoning, right?
Oh, without a doubt.
But they are developing this hidden dangerous side effect. They are becoming overwhelmingly cocky.
Yeah, it is the absolute definition of a double-edged sword in current generative AI training.
Right?
We were pushing the boundaries of what these systems can compute, but in the process, we're accidentally erasing their ability to just say, I don't know.
Which brings up a really basic question. How do we even measure an AI's self-awareness in the first place?
That's the million-dollar question.
Like, if I'm a developer, or even just you listening, relying on ChatGPT for research, how do you actually quantify whether the AI knows it's right versus when it's just, confidently making things up?
Right. So we measure that through a core metric called model calibration.
Model calibration. Okay.
Yeah. In the simplest terms, model calibration is the mathematical correlation between a model's confidence in its own answer and the actual ground truth correctness of that answer.
Got it.
We are essentially asking, does the model actually possess internal doubt when it is generating a wrong answer?
And for you listening, think about why this matters in the real world. If you are deploying an AI in high-stakes domains, let's say it's analyzing a company's financials for a massive merger or screening patient records for a medical diagnosis.
Right. Situations where you cannot afford a mistake.
Exactly. You desperately need that system to reliably estimate its own uncertainty. You want it to flag a human doctor or a financial officer for help rather than hallucinate.
Yeah, hallucination being when it generates a plausible but factually incorrect assertion.
Right. So how do we actually look inside the AI's brain to see that doubt?
Well, to measure that confidence, we look at a concept in large language models called perplexity. Yeah. Perplexity is basically a measure of the model's intrinsic uncertainty during the free-form generation of text.
So as it's typing out the words, word by word.
Exactly. Lower perplexity means higher confidence. The model's internal statistical engine is essentially saying, I am statistically very sure of the next word I am generating.
Okay, so if the model is perfectly calibrated, we want low perplexity when the answer is correct and high perplexity when the answer is wrong.
That is exactly the goal.
Yeah.
And the researchers in this paper focus on evaluating that using something called relative calibration.
Okay, how does that work?
They use a metric called AUC, or area under the curve.
I've heard of that.
Yeah, it's pretty common in statistics.
Yeah.
Imagine you take every single answer an AI generates and you line them all up in a row. You sort them from the ones it was most confident in all the way down to the ones it was least confident in.
Okay, so the lowest perplexity answers at the front of the line and the highest perplexity ones at the back.
Yes, exactly. The AUC metric tests whether all the correct answers naturally cluster at the front of that line.
Oh, I see.
And all the incorrect answers naturally get pushed to the back. It calculates the pairwise separability, meaning if you randomly pick one right answer and one wrong answer from the pile, does the math under the hood show that the model was more confident in the right one?
Okay, so if we have this incredibly clear, objective way to measure an AI's self-awareness, why are our current best models failing at it? Because the paper points out a pretty terrifying trend, right?
Yeah, it's very concerning.
As we train these models to get smarter, they are getting worse at this exact metric.
Yeah, the problem really stems from the status quo of how we currently teach models to reason.
Okay.
Right now, the absolute state-of-the-art methods for training reasoning in language models are algorithms like GRPO,
Which stands for?
Group Relative Policy Optimization, and there's also GSPO. They use reinforcement learning.
And what did the Tsinghua researchers actually find when they looked under the hood of those training methods?
Well, they tracked the entire training lifecycle of a model using GRPO. And as the training progresses, the model's accuracy on complex math problems goes up steadily.
Which is what we want.
Right, it objectively gets better at solving the math.
Yeah.
But at the exact same time, that relative calibration, the AUC metric we just talked about,
Yeah.
it progressively and steadily worsens.
Wait, hold on. That doesn't make any sense.
I know, it's a paradox.
If we're rewarding the model for getting the math problem right, shouldn't getting smarter inherently make it more calibrated? I mean, why on earth would it become more confidently wrong on other problems?
So if we connect this to the bigger picture of how the algorithm actually functions, the flaw reveals itself.
Okay.
The paper provides this really rigorous mathematical proof showing that this degradation isn't a fluke. It is a hard-coded feature of the training dynamic.
A feature, not a bug.
Well, an unintentional feature. It comes down to the fact that GRPO uses a reward-only sample evaluation.
Meaning it only grades the final answer.
That is the core issue. During training, GRPO gives the model a really complex math question, and the model generates a grip of different answers.
Okay.
The algorithm then scores those answers purely based on whether the final extracted number is right or wrong. It's a simple binary 1 or 0.
Right.
It then compares the rewards within that group to create an advantage score. So if response A gets a 1 and response B gets a 0 way.
Response A is given a positive advantage and B gets a -1.
Exactly.
Okay, so it's like a game show host who only cares which contestant hit the buzzer and yelled the right answer the fastest.
That's a great way to put it.
Right, the host completely ignores the quiet contestant who, carefully did the math on a notepad but maybe hesitated for a second. The system only rewards the loud, aggressive guesser, so all the AI models just learn to be loud, aggressive guessers.
That is a brilliant analogy. By completely ignoring that hesitation or the internal uncertainty, the algorithm optimizes for the wrong thing entirely. The researchers explain the GRPO's mathematical direction, like the way it updates the model's brain, aligns with an inconsistent surrogate for calibration.
Wait, surrogate. Surrogate usually means a stand-in for something else. What is the algorithm using as a stand-in, and why is it failing so badly?
Well, in machine learning, you often can't directly optimize for a complex sorting metric like AUC because the math is non-differentiable.
Meaning it's too jagged or blocky for the computer to understand.
Exactly. It's like trying to program a car to drive up a jagged staircase. The computer needs a smooth hill to calculate its trajectory.
Right, the gradients.
Yes. So engineers create a surrogate loss, which is a smooth mathematical hill that approximates the staircase. But GRPO uses an inconsistent stand-in.
Because it's only looking at the binary game show buzzer.
Right. Because it only looks at the win or loss of the buzzer, it incentivizes the model to push its confidence to the absolute maximum for anything that even looks like a correct answer.
It learns that being highly confident is strongly correlated with getting the reward.
Yes. So it artificially sharpens its output distribution across the board. The perplexities of both right and wrong answers decrease concurrently.
Oh man, it just becomes a louder, more confident liar.
Exactly.
If the game show host never penalizes false confidence, the learning process is optimizing for reward, not for honesty. But surely people have realized this before now. I mean, haven't there been attempts to fix this overconfidence?
Oh, there have been several. The paper highlights previous attempts with names like CODAPO, CDE, and SIMCO.
Okay. Did they work?
Not really. Those past fixes mostly relied on heuristics.
Like rules of thumb.
Right. They were clever workarounds, like artificially smoothing the labels or manually tweaking the reward shapes, rather than addressing the fundamental mathematical flaw in the surrogate itself.
And if you don't fix the foundation, the house still collapses.
Exactly. The paper highlights that one of those heuristic methods, SIMCO, tried to fix the overconfidence but ended up severely damaging the model's actual reasoning capability.
Like, how bad was the damage?
Shockingly bad. SIMCO dropped the model's raw accuracy by nearly 12% on the AMC math benchmark compared to the baseline.
12%.
Yeah, it basically made the model second-guess itself so aggressively that it forgot how to do the math it had already learned.
That is wild. So if heuristic band-aids like SimCode just destroy the model's accuracy, we can't just patch the system. We literally have to rewrite the foundational math.
We do.
So how did the Tsinghua team actually do that with CAPO?
They developed a two-part solution. CAPO stands for Calibration-Aware Policy Optimization, and the first part directly attacks that game show host problem.
Okay, I'm listening.
CAPO adopts an uncertainty-aware advantage estimation based on a logistic AUC surrogate loss.
Okay, surrogate loss. I get we just said GRPO used a bad, jagged stand-in, but what does the logistic part actually change under the hood?
Right, so the logistic function creates an S-curve. It takes raw, unbounded scores and smoothly translates them into a probability between 0 and 1.
Oh, so it's not just 0 or 1 anymore.
Exactly. By replacing the binary pass-fail system with this logistic curve, the algorithm can suddenly compare the degree of the model's confidence against the reality of its correctness.
That makes so much sense.
And the beauty of this specific logistic formula is that it is theoretically consistent. The researchers proved it admits a regret bound.
Okay, let's translate that for the listener. A regret bound, that means there's an actual mathematical guarantee, right?
Yes, it guarantees that every single step the algorithm takes up that smooth hill directly translates to climbing the actual staircase of the AUC metric.
It's no longer a heuristic guess.
Not at all. When the algorithm updates the model's weights using this new logistic formula, it actually scales the update based on the confidence gap. It prioritizes fixing the specific responses where the AI's confidence was out of alignment with reality.
Let me make sure I'm following this. If the model gets the right answer, but its internal perplexity was high, meaning it was secretly very confused and just got lucky, this new formula flags that. It says, hey, you got it right, but your internal logic was a total mess. Let's fix that uncertainty.
Exactly right.
And conversely, if it gets it wrong but was highly confident, it punishes that specific blind arrogance aggressively.
That is exactly how the mathematical penalty works. It forces the model to reconcile its internal doubt with its external output.
That is brilliant.
But the researchers didn't stop there.
Oh, there's more.
Yeah. They knew that even with perfect math, the training data itself can be incredibly messy. Which brings us to the second mechanism, denoising via reference model-based masking.
Okay, here's where it gets really interesting. Because when you are training on thousands of complex math problems, marking things purely right or wrong introduces massive gradient noise.
It does.
Like sometimes the AI uses brilliant, flawless logic for 10 steps, but makes a tiny typo at the very end. The binary reward marks it as a total failure, a 0.
Yep. And on the flip side, sometimes the AI outputs complete garbage logic, just hallucinating numbers wildly, but by pure dumb luck, it guesses the final multiple choice letter correctly.
Right. And the system marks that as a huge success.
Exactly. Training a model on that kind of noise risks punishing good reasoning and rewarding spurious lucky guesses.
So how does CAPO filter out that noise?
It uses upper and lower limits, which the paper calls ref high and ref low.
It's exactly like a math teacher grading a final exam, really.
That's a perfect analogy.
Instead of just looking at the multiple choice bubble the student filled in, the teacher walks over and looks at the scratch pad.
Right.
If the student bubbled the right answer, but the scratch pad is filled with incoherent gibberish, which the model measures as high perplexity, the teacher says, you guessed, you don't get credit for this. That's the ref high limit.
Exactly. And conversely, if the student got the final answer wrong, but the scratch pad shows deep, coherent reasoning, meaning low perplexity,
The teacher gets partial credit.
well, the teacher says, you made a small typo, but your logic is completely sound. I'm not going to punish your reasoning skills for a clerical error. That's the ref low limit.
That is so smart.
And CAPO uses the original untrained base model's perplexity to evaluate that scratch pad and simply masks these noisy samples out of the training update entirely.
Wait, it just ignores them.
It just ignores them. It says, this specific data point is too confusing or contradictory to learn from. Let's skip it and focus on the clean data.
That is an incredibly elegant approach.
It really is.
Yeah.
It uses the base model's inherent baseline calibration to filter out the gradient noise. It stabilizes the entire training process without requiring any massive external reward models or additional training overhead.
So it's essentially computationally free.
Pretty much.
So the foundation is completely rewritten. We have a mathematically airtight logistic surrogate with a guaranteed regret bound, and we have a clever masking mechanism to act like a teacher checking the scratch pad.
Yeah.
But, theory is just theory. What happened when they actually put this to the test?
Oh, they put CAPO through an absolute gauntlet.
They did.
The researchers tested it on Quen 2.5 math models, specifically the 1.5 billion and 7 billion parameter versions, and they ran them across 6 brutal math benchmarks.
Which ones?
We're talking AIM 2024, AIM 2025, Math 500, AMC, Minerva, and Olympiad bench.
Wow, so complex, multi-step, Olympiad-level reasoning challenges.
Exactly.
And the numbers, did they actually prevent that calibration collapse that GRPO suffers from?
They didn't just prevent it, they reversed it entirely.
Really?
Yeah, KPO steadily improved calibration throughout the entire training life cycle. On the AM 2025 benchmark compared to the GRPO baseline, KPO boosted the relative calibration that AUC metric by up to 15% for the 1.5 billion parameter model.
That is huge.
And for the larger 7 billion parameter model, it boosted calibration by roughly 25%.
25%.
They took the AUC from 0.54 all the way up to 0.79.
Wait, a 25% jump in calibration. That's a massive leap in self-awareness. But did it have to sacrifice its basic reasoning speed to get that kind of honesty? Did it drop 12% of its accuracy like Simcoe did?
Not at all. And that is really the holy grail of this research. It achieved these massive calibration gains while matching, or in several cases beating, GRPO's baseline reasoning accuracy.
It proved that a model can be rigorously honest and exceptionally brilliant at the exact same time.
Exactly.
It's incredible. But for you listening, you might be wondering how a high AUC score on a math test actually translates to the real world. Like, what does this all mean for the user?
There are 2 major tangible benefits.
Okay, let's hear them.
What's fascinating here is how calibration unlocks pure performance gains during deployment. The first benefit is hallucination mitigation. Because KPO models have such high calibration alongside high accuracy, they achieve what the paper calls a Pareto optimal precision coverage trade-off.
Okay, let's decode Pareto optimal. What does that actually mean for the listener using this AI?
It means the AI hits the mathematical sweet spot. It can answer as many questions as possible without compromising its accuracy.
Ah, I see.
If a model actually knows when it is confused, you as the developer can set a firm confidence threshold. If the AI's internal confidence falls below that line, it simply abstains from answering.
It reliably says, I don't know, instead of lying to you.
Right, which protects the integrity of the entire system.
No more confidently fabricated data from the cocky analyst.
Exactly.
But there's a second massive real-world application here, isn't there? Something called inference-time scaling.
Yes. The industry standard right now for solving incredibly complex problems is a technique called best-of-n scaling.
Let's walk through that. What does a best-of-n scenario actually look like in the real world, and why do we use it?
So when you have a really tough problem, instead of asking the AI for one single answer, you ask it to generate n number of candidate responses.
Like brainstorm a bunch of ways to solve it.
Right. You might ask it to generate 16, 64, or even 256 different ways to solve the problem. Then you aggregate all those responses, and the system automatically picks the one the model is most confident in.
Let's put that in perspective. Imagine you're a doctor using an AI to analyze a complex patient blood panel alongside a list of rare symptoms.
Okay.
You feed the data into the AI and tell it to generate 64 potential diagnostic pathways. If you are using an uncalibrated model trained on GRPO, what happens?
You get a disaster.
Yeah.
An uncalibrated model might generate 50 variations of a common cold diagnosis with wild, misplaced confidence, and only a few variations of the actual rare autoimmune disease.
Because it's a loud guesser.
Right. Because the model doesn't understand its own uncertainty, it assigns massive confidence scores to the wrong answers just because they look fluent.
And if the system picks the answer with the highest raw confidence score from a broken algorithm,
The doctor is handed a highly convincing, totally incorrect diagnosis. It's just picking the loudest lie out of the lineup.
but with CAPO, because the perplexity scores are mathematically aligned with true correctness, the AI can accurately sift through those 64 answers.
Exactly.
It can look at the common cold generations, realize its internal mathematical logic for those was actually incredibly weak and high perplexity, and just discard them.
Yep.
And it can elevate the rare disease diagnosis because it recognizes that the underlying reasoning for that specific path was incredibly sound. It accurately grades its own homework.
And the results of that capability just speak for themselves. The paper shows that on the AIM benchmarks, using this best-of-n inference-time scaling, CAPO boosted downstream accuracy by up to 5% over the GRPO baseline.
Wow.
That is a free 5% boost in pure reasoning power, unlocked entirely because the model's confidence scores finally mean something real.
It fundamentally changes the utility of the model.
It does. You aren't just getting a higher volume of answers. You are getting a mathematically reliable signal of when to trust those answers.
So, to summarize the journey we've been on today, we started by looking at the dangerous status quo, right? Current state-of-the-art training methods like GRPO are fantastic at making models smart, but terrible at keeping them honest.
Right. Their game show buzzer math creates an inconsistent surrogate that rewards blind confidence.
Which leads to severe calibration collapse.
Exactly. And we explored how KPO completely rewrites that foundation.
Yeah.
By introducing a theoretically consistent logistic surrogate, it provides a mathematical guarantee, a regret bound, that the training process will actually improve calibration.
Paired with that brilliant masking system that acts like a teacher checking the scratch pad to filter out lucky guesses and unlucky typos.
Which stabilizes the entire ecosystem.
The result is an AI that dominates complex Olympiad benchmarks, not just in raw accuracy, but in knowing the exact statistical boundaries of its own capabilities.
It mitigates dangerous hallucinations and boosts inference scaling, all without adding any extra compute overhead.
It's a massive step forward in building AI we can actually trust in those high-stakes environments.
It really is. But this raises an important question, though, a final thought for you to mull over as we wrap up.
Okay, let's hear it.
If we successfully deploy methods like KPO across all generative AI, we will very soon have artificial intelligence systems that possess a mathematically perfect understanding of their own limitations and ignorance.
Right.
They will know exactly, down to the decimal point, when they are guessing.
Which is something human beings are notoriously terrible at.
Exactly. Will that mathematically guaranteed self-awareness eventually make us trust AI systems more than human experts?
Oh, wow.
I mean, after all, humans famously struggle with their own overconfidence. We rarely know the exact statistical boundaries of our own knowledge.
It's a wild thought. We started this deep dive by talking about that brilliant but dangerously cocky human analyst giving you fabricated data.
Yeah.
It turns out fixing the AI's ego was just a matter of rewriting the optimization math. Fixing human overconfidence, well, that's a much harder equation to solve.